Alright, so since we used that as an example while we were doing the cars in the last one, I thought it would be a good idea to go ahead and actually do this problem for you as another example where we have these trains moving in different locations, because this is a classic problem that you do see. And again, just to recap what's going on here, we have one train that's traveling west toward Denver. So this is our train traveling west toward Denver. They give us a speed, 2 miles per minute, also known as 120 miles per hour. We have another train that's traveling north away from Denver. So this must be Denver right here. It's traveling north away from Denver, and they give a speed for that one, 1.5 miles per minute. So you're given rates, and then they're giving you that at a certain time, at an instant, the train is 20 miles east and the second is 10 miles north. And then they're going to ask you to calculate the rate at which the distance between the trains is changing when t equals 0, when t equals 10, and then to kind of basically take a look at what's going on with the situation to work with it. So just like in the problem that we did with the cars, and again, just kind of showing you, we'll do the little illustration here, that as we move through, the distance is changing over time. Now, this is getting not a perfect curve because I'm varying my speed a little bit as I go, but you can see that in the beginning, the trains are getting closer together, and then they're getting farther apart. Okay, so at t equal to 0, at that instant, when the cars get to that point, if you look at this, it should not surprise us that we're going to have a negative rate here. But at t equal to 10, the next instant they ask you to calculate, we should end up with a positive rate when we do the calculation. All right, so we're going to come over to this version over here as I have, and we're going to start creating our problem. And remember, I'm not going to worry about the instant down here, t equal to 0 or t equal to 10 yet. I'm going to label these as variables because they're changing. I'm going to call this x, and I'm going to call this y. All right? And the distance between them, I'm going to call it h, just like I did in the problem. So our initial thought here is, kind of the same idea. Our h is our distance between. And in this problem, we are still doing our miles. We are trying to find dh dt. Okay. We're going to define x, and again, I'm going to do it as position on the x-axis, and it's going to be in miles. But now here's where you want to be careful. Your position, this train is traveling this way. What's happening to your position over time? As we moved, it is getting smaller, so it's decreasing. So when I do my dx dt, based on the location of where the train is going, that train, the 2 miles per minute, I'm going to go with miles per minute because it said t is in minutes. So it's going to be 2 miles per minute, but I need to make sure that I put this as -2 because this position is decreasing. When I do my y, position on the y-axis in miles, my dy dt that we're going to be using, this value, because the train is moving toward the north, moving up, that is going to give us a positive value for the train. So that would be positive 1.5 miles per minute. Okay, so then we basically want to calculate what's the rate that the distance is changing when t equals 0. So let's do part A. I'm just going to slide down just a little bit so I have room. Or number 1 here. Now for number 1, actually for both problems, our quantity formula is the same for both. So I'll go ahead and jot that down. X squared plus y squared equals h squared. Then my related rates formula is going to be the same for both. 2x dx dt plus 2y dy dt equals 2h dh dt. And now for number 1, let's start plugging and chugging. All right. When t equals 0, what do I know about my positions? The first train is 20 miles east of Denver. So I'm right here at 20, and that position would be x equal to 20. My second train is 10 miles north of Denver. So y, 10 miles north of Denver, would be positive 10. So I'm getting my values that I need to plug in. And then we have our rate for dx dt and dy dt. And then the problem is I now need h. I'm looking ahead. I need h to plug in. H is the square root of 20 squared plus 10 squared. All right, so that's going to be the square root of 500 or 10 square root of 5. So I get all my values, and I'm going to take my related rate formula. I'm going to plug in what I know. 2 times 20 times dx dt, which was negative 2, plus my 2y times my dy dt, which was 1.5. I'm going to write it as 3 halves because that'll make it easier to calculate. And then equals to the h that we just found, 10 square root of 5, times dh dt, which is what I'm trying to solve for. Right, I'm going to leave you to verify that you should get dh dt is negative square root of 5 over 2, I believe. And that would be in units of miles per minute, okay, because everything we put in, we made sure our units matched. Does it surprise us that that's a negative value? No. If you look up here at 0, and I look at the slope of the distance curve, it is decreasing, so it should have a negative slope, so that should make sense to us. All right, and then for number 2, we are going to repeat the process. The difference here is now we are when t equals 10. All right, and remember that's 10 minutes later. So we need to figure out what position we are at 10 minutes later. So this actually requires a little bit more work. We have to remember that our first train, the train that is on the x-axis, is traveling toward the west at this 2 miles per minute. And so what happens if I'm basically moving this place 2 miles per minute? How far have I moved in 10 minutes? In 10 minutes, we have gone 20 miles back in that direction, so our position is actually x equal to 0, because I've moved 20 miles back, and I'm actually at Denver. Okay? And then when t equals 10 minutes, my y was moving at 1.5 miles per minute, and we've gone for 10 minutes. That would be 15 miles. So this train, it was at 10 and it's gone 15 more miles in this direction, so you would be at a position of y equal to 25. Okay, so I did have to do a little work to figure out where I was. And my h at that time, because you're going to need that to plug in, remember up here, would then be square root of 0 squared plus 25 squared, or 25. So now I have everything I need to plug and chug, so we basically put everything in. We have our 2 times our x, which is kind of nice, times our dx dt, plus 2 times our y, times our dy dt, which was 3 halves, equals 2 times my h times the dh dt that we're trying to solve for. So this, of course, goes away, and we can very quickly see we get 75 equals 50 dh dt, so dh dt equals, divide by 50, 3 halves. And so that would be 3 halves miles per minute. And again, that should not surprise me that that is a positive value, because over here at 10 minutes later, you're over on this side, I have a positive slope to my distance function. The distance is increasing over time. All right, and then just also kind of taking a look at that, do you think it was coincidental that you ended up getting 3 halves, which did happen to be your change in y the same value as that? Why did it end up being that the change in the h was the same as the change in the y at that moment in time? If I go back to the picture that moves here, and so as we're kind of working our way and letting the curve change, when we hit the 10, see if I can get myself right on the 10 here. Not quite, but close enough. When I get to this and it is exactly 10, the distance between the vehicles is exactly the distance that is y. So it shouldn't surprise us that we actually, if we realize that, would not have had to actually do the work. However, it's always good practice to do the work. So that ends up that next example, just another example of where we have the trains or cars moving toward each other, because that's always an interesting one to work with. All right, and then just to be thorough in this problem before we leave it, here's my answer to number 3, that when t was equal to 10, the h and the y were referring to the same distances, that h and y were both at this position. And so since they were both in the same place and referring to the same value that was changing, then at that instant it should be obvious that dh dt and dy dt would have been the same at that very instant. All right, so that's the end of that problem.